Today's video is going to be smaller than usual, especially because this is the last video before the exam. I'll finish off the chapter and introduce one more concept which is not in the book, but which is quite important. Okay, last time we saw that if f is a monotonic function, then the set of points on an interval AB where f is discontinuous is at most countable. Okay? Remark. It should be noted that the discontinuities of a monotonic function need not be isolated. The discontinuities of a monotonic function need not be isolated. In fact, the set, while it's countable, can even be dense. Okay? In fact, given any countable E, which is a subset of AB, even if it's dense, we can construct an F. Construct F on AB, which is discontinuous at every point of E. And continuous everywhere else. Continuous everywhere else. Okay? Such an F is not unique. We'll show one construction. Okay? So, arrange the points of E. Arrange the points of E in a sequence xn. But if it's finite, then there are finitely many. If it's infinite, it's still countable, so you can write it in a sequence. Let Cn be a set of positive numbers. Be a set of positive numbers such that summation Cn converges. Okay? Note, since Cn's are all positive, this is saying that Cn converges absolutely. Okay? Then define f of x is equal to summation xn smaller than x Cn a smaller than x smaller than b. Okay? So, note, as summation Cn converges absolutely, the order does not matter. Okay? Now, it is easy to see that the three following properties are easy to see. the following properties hold. First, f is monotonically increasing on A to B. Second, f is discontinuous at every point of of E at every point of E. In fact, at any point xn, we have f of xn plus minus f of xn minus is equal to cn. And third, f is continuous at every other point. F is continuous at every other point in maybe. Okay. I'm not going to prove this, but should be able to convince yourself. If you're not, try to prove it. Right? F is monotonically increasing because summation Cn xn is smaller than Cn is always strictly increasing. Right? You're only adding positive terms and you're adding more and more every single time. Also, it is continuous at every other point. It's going to be more or less constant at every other point. Okay? You can always find, if you find a small neighborhood where if E was not dense, then you could find a small neighborhood in which there are no points of E, and the function is going to be constant in that. Okay? Then let us look at the final section in the book, and then one more idea from outside the book. At least in the book, it's not defined right now. Infinite limits and limits infinity. So for any real number, we defined a neighborhood of the real number as x minus delta, x plus delta, for a small, for some delta, right? It's a ball of radius delta. Okay. Now, if I want to define limits at infinity, I need to be able to define, there is no x minus delta, x plus delta at infinity. It makes no sense, right? So I need to define some neighborhood at infinity. So definition, for any real C, for any real C, set the set of numbers x such that x is greater than C is called a neighborhood of plus infinity and is written C comma plus infinity. Similarly, the set minus infinity comma C is a neighborhood of negative infinity. Okay. Definition. Let f be a function defined on E. Function defined on E subset of R. We say f of t approaches a as t approaches x. Now, in extended real system, where a and x are in the extended real system, if for every neighborhood of u, if for every neighborhood u of a, there is a neighborhood v of x, there is a neighborhood v of x such that v intersection e is not empty, and such that f of t belongs to u for all t belonging to v intersection e, t is not equal to x. Okay, we are extending the definition of limit since we cannot define distance at infinity. Okay, we are defining it in terms of neighborhoods. Okay, now this definition would work even on places where they are not metric spaces. Okay, so this is the standard definition of limits when you're looking at things that are not metric spaces, but you have a topology defined on it, which is to say you have open sets defined on it. Okay, we're not going to go into it because this is a course in real analysis. You're only dealing with metric spaces, not a topology. Okay, but same way as definition of continuous was inverse image of open set is open, this is the standard definition of limit for spaces which are not metric spaces. Okay, in that case we have theorem 4.34, which is a generalization of the results for just real numbers. Let f and g be defined on E subset of R, and suppose f of t goes to A, g of t goes to B, as t goes to x. In that case, then the following results hold true. Just say f of t goes to A prime implies A prime is equal to A. Just say the limit is unique. F plus g of t goes to A plus A prime. A plus B, sorry, not A prime. See, f times g of t goes to A times B, and D f divided by g of t goes to A times B, A divided by B. Okay, provided the right the RHS of B, C, and D are defined. which is to say, note, we have no idea what infinity minus infinity, 0 times infinity, or infinity divided by infinity, as well as before anything divided by 0 are. So these are not defined. Okay. I'm not proving this. The results hold for exactly the same reasons as for previous things. Okay. Instead, let me define some more interesting concepts which are quite useful. Okay. Which are pointwise and uniform convergence for real valued functions. Uniform convergence. For real valued functions. Okay. Definition. So you're looking at functions, right? Functions, you can define a lot of functions. You can define addition of functions and everything. So why not limit of functions? So let X be any set, not necessarily a metric space. Let X be a set, and Fn be a sequence of functions. Fn be a sequence of functions defined on X. Defined. Okay. Sequence of real valued functions. Real valued functions. Defined on X. Okay. If for each X belonging to X, that's right, X belonging to E, which is a subset of X, the limit limit n goes to infinity, Fn of X exists, then we say, then we can define the pointwise limit. Then we define the pointwise limit of uh, of Fn by f of X is equal to limit X goes to n goes to infinity, Fn of X for each X belonging to E. Okay. And say Fn converges pointwise to F on E. Okay. So the question is, what information do we get about F from Fn. For example, uh, if Fn is continuous for each f, for each n, then is f continuous. Then is f continuous. And as much as we would like that to be true, here's an example where it fails. So that is not true. Even if Fn is continuous for every Fn, life is not as great. Okay? So example, for n belonging to n, let Fn is equal to Fn from 0, 1 to 1 to Rn be defined by b Fn of x is equal to just x to the n. Okay? Then Fn is continuous for every single n, right? X to the n is continuous for every single n, right? However, what happens? We have seen sequences. We know that then for x belonging to 0 to 1, limit n goes to infinity of Fn of x is equal to 0, while limit n goes to infinity Fn of 1 is equal to 1. Hence, the pointwise limit is given by is given by f of x is equal to 0 if x belongs to 0, 1, and 1 if x is equal to 1, and this is not continuous. Clearly, f is not continuous. Even though Fn are all continuous. Even though Fn are continuous everywhere. Okay. So we need to define something slightly better if you want the limit of continuous functions to be continuous, you would want some better definition. Right? The definition we are going to go for is the definition of uniformly continuous. Uniform convergence. Uniform convergence of functions. Okay? Let Fn from x to r be functions. We say Fn converges uniformly to a function f on E subset of x if for every epsilon greater than 0 there exists an n belonging to n such that n greater than or equal to n implies absolute value of Fn of x minus f of x smaller than epsilon for every x belonging to E. Okay? So compared to pointwise convergence, this is a stronger definition of convergence. And this is more or less following the idea of, was it uniform convergence? What did we call it? What is it called? For sequences, it is I can't remember what uniformly continuous. For a function, we called it uniformly continuous, right? Yeah. So this is more or less the idea that is generalizing, or not exactly generalizing, adapting the idea of uniformly continuous. Okay? We say that the same n should work for every x in E. Okay? So this is more or less the difference between continuous and uniformly continuous. This is more or less the same idea as pointwise convergence to uniform convergence is the same kind of idea as convergence is to uniform convergence. Okay? So it is clear that uniform convergence implies a pointwise convergence. Uniform convergence implies pointwise convergence. Okay. However, the converse is not true. However, the converse is not true, which we will elaborate with the next result, which will show that, oh, this definition does the work that I wanted to do, which is to say, if I take a sequence of functions fn and they converge uniformly, then if fn were continuous, then f should be continuous. Okay? So before that, I'm going to show one result. Proposition. Assume fn converges to f pointwise. Okay? On E, and put mn is equal to supremum x belonging to E fn of x minus f of x. Assume additionally that mn is smaller than plus infinity for every n belonging to n. Okay? Then fn converges to f uniformly if and only if mn goes to 0 as n goes to 0, as n goes to infinity. Proof. Okay, before we give the proper proof, let us see why it should work. What is the idea that it should be working? Why should it work? In uniform convergence, we are trying to say that, oh, the same n should work for every single x, right? So if my function does converge uniformly, given a delta, given an n, all of this should be less than epsilon. So given an epsilon, there should be n such that supremum of this should be less than epsilon for every x. Well, fn minus f should be less than epsilon for every x, so the supremum is less than epsilon. So eventually it should go to 0, right? Conversely, suppose this limit goes to 0, then there should be an n such that the supremum is smaller than epsilon for that n for everything after that n, which is satisfying the definition of uniformly convergent, right? So the systematic proof is just formalizing that. Assume Fn converges to F uniformly. Choose epsilon greater than 0. And pick n belonging to n such that n greater than or equal to n implies Fn of x minus f of x smaller than epsilon over 2 for every x belonging to e. Well, I mean, technically I don't need epsilon over 2, but let me take it there anyway. Then n greater than or equal to n implies mn, which is the supremum of x belonging to epsilon, f belonging to e, fn of x minus f of x. Well, you have seen that this is smaller than or equal to epsilon over 2. So if I had just taken exactly epsilon, that could have been exactly equal to epsilon, which is the problem. However, this is smaller than equal to epsilon, but it's still smaller than epsilon over 2. So it's smaller than epsilon. So n goes to 0. As n goes to infinite. Other way around. Assume mn goes to 0. Choose epsilon greater than 0. And then pick n belonging to n such that n greater than or equal to n implies mn is smaller than epsilon. Then n greater than or equal to n also implies f of n fn of x minus f of x, well, which is clearly smaller than mn, which is smaller than epsilon. Therefore, fn converges to f uniformly on E. Okay? That's the proof. Now, let us show the important result, which is why we even defined this. Theorem. This is called the uniform limit theorem. Let Fn be a sequence of continuous real valued functions valued functions on a metric space X on a metric space X with distance D. Assume f from E to R is a function such that Fn converges to F uniformly on E subset of X. Then F is continuous. Proof. Given epsilon greater than 0, so let epsilon be greater than 0, and X belonging to E. We want to show there exists a delta greater than 0 such that distance of x comma y smaller than delta implies f of x minus f of y smaller than epsilon. Right? If y belongs to E. Right? What we are going to do is we will use f of x minus f of y is smaller than or equal to f of x minus fn of x plus fn of x minus fn of y plus fn of y minus f of y. Okay? And we are going to do so, and we are going to try breaking all so that all three of these are smaller than or equal to epsilon over 3. Smaller than or equal to epsilon over 3. That's our goal. Get these smaller than or equal to epsilon over 3. And we are going to do this. Choose n such that n belonging to n such that f of z minus fn of z is smaller than or equal to epsilon over 3 for every z belonging to E. Okay? Then, for the same n, choose delta greater than 0 such that distance of x comma y is smaller than delta and y belonging to E imply fn of x minus fn of y smaller than epsilon over 3. Okay? In that case, then for all y belonging to epsilon such that y belonging to E such that distance of x comma y smaller than delta, we have f of x minus f of y is smaller than or equal to f of x minus fn of x plus fn of x minus f of y plus n of y minus f of y smaller than or equal to epsilon over 3 plus epsilon over 3 epsilon over 3 which is equal to epsilon as required. Okay. Where are we using uniform convergence rather than pointwise convergence in the proof? We are using it in knowing that for n belonging to n, for the same n we can choose delta such that this happens. Okay. The problem is if you just choose pointwise convergence, then sure you can choose an n such that f of z minus you can choose an n such that it holds for x, but then you have to choose a different n such that it holds for y. The same n might not work for both, and then you have to choose a delta. Well, the delta depends on n, and the n depends on y, and the y depends on delta. So you might not be able to choose all three of them simultaneously. Okay? If you want to try it out what is going wrong, you can try working it out for what happens with a given sequence x to the n and and 0 to 1 and see where it fails. Okay, I am going to stop this video here. This is all that we are going to cover for exam 2. Okay, I'll try to put a review sheet for exam 2 up by today evening. And yeah, exam 2 will again have similar timings available. The two timings will again be exactly the same, either the class timing or the evening timing. I'm going to open registrations for both the groups again. Okay, I'm going to delete the old groups and open registration for groups again. Please register in whatever group comfortable to you.